Okay, now chapter 7, integrals and transcendental functions. This chapter will begin with redefining the logarithm function as an integral. Then we'll study exponential change and separable differential equations. After considering hyperbolic functions, we'll deal with relative rate of change in terms of big O and little o. Let's go to section 7.1. The logarithm defined as an integral. The natural logarithm is the function given by this equation. We already know that antiderivative of 1 over t is same as natural logarithm absolute value of t plus c. If we evaluate the term from 1 to x, then you can get logarithm x for positive x. We may consider this equation as another definition of logarithm x. Then we can get such an interpretation. And for the curve 1 over t, y equal 1 over t, the integral means that there's area between 1 and x. So the area here, that is now logarithm x. Once x is negative, less than 1, then area must be negative, as in this figure. So along with this definition, another definition, we can get here, we can interpret logarithm x in terms of the area. Now, once we define logarithm in this way, then from the first part of fundamental theorem of calculus, logarithm x is continuous and differentiable. If we differentiate logarithm x, then here we can get 1 over x. Okay, also we can redefine number e along with that definition. Once we are replacing x with e, then okay, and then logarithm e will be 1, so that from 1 to e, an integral is 1. That means that here, if you are choosing that e is the number such that the area under the curve is 1. So in this case, area is 1. We can get e in such a way. So we may consider it as another definition of e. Okay. Okay, here we have a recall from section 4.8. Integral of 1 over x is the same as logarithm absolute value of x plus c. If u is a differential function and non-zero, then 1 over u integral with respect to u is same as logarithm absolute value of u. If u is f of x, then here f of x, and du must be f prime x dx, so that it becomes in this way, and then u is now f of x, so we can get such a formula. We'll practice this formula in the following examples. Okay, here, if we consider this as f of u, then that is now constant multiple of f prime of y. And here, okay, let's say f of y equal y squared minus 25. Then f prime y is same as 2y. So that y dy is half of that. So that is in half of f prime of y. We can write in this way. Here, that is integral. Given integral is same as integral, bottom is y squared minus 25, top one, okay, let's try to change this one with 2y so that it becomes f prime y, and to make it the same, we have to put half in front of that. Then we know that from this one here, half is there, and then that is now natural logarithm of y squared minus 25 and plus c. That's it, right? And also same way, if we consider this is bottom is f of x, then f prime is same as now, okay, 3, derivative of sec is same as sec x and tangent of x. Okay, so here the given integral can be written in this way, integral and 2 plus 3 sec x on the bottom, and its derivative is now 3 and sec x and tangent to x and dx. Now extra term is 3, so we have to put here now 1/3, then they are the same. Okay, now by using the formula, that is 1/3, and this portion is changed into natural logarithm of now 2 plus 3 sec x, right? And then plus c. Okay. Okay, now we'll practice substitution methods here. And for this integral, we may start with now u substitution along with u becomes logarithm and cosine of x. Then du will be here now. And here substitution is along with logarithm, so that in fact we are practicing right now. Here logarithm f, the derivative of logarithm f is same as f prime over f. Okay. Now f prime, okay, the bottom must be f of x, and top is derivative of that, that's minus sine x, now dx. So that is same as minus tangent of x dx, so that this portion over there then must be same as minus du. So here the given integral is the same as now logarithm cosine x, that portion is same as u, and then remainder part is same as minus du. So here minus 1 will go out, and then antiderivative of u is half u squared, so that we can get here minus half, and u is here logarithm cosine of x and squared plus c, right? Also for this one, now that term can be u. U is logarithm of x. Then here du must be, okay, in the bottom f of x and its derivative, okay, that is same as now 1 over x logarithm x dx. Okay, quite simply this portion is same, becomes now du, so that given integral is same as integral u du, that is half u squared plus c. Now you can replace u with that term, then that's it, you can finish it. Okay, for that one, now, okay, for this one, you may think here now u equal minus 1 over x squared that is same as minus x to the minus 2. Then du must be same as, okay, here becomes 2 and x to the minus 3 and dx. So that portion, okay, this portion is same as half du. So here, given integral is changed into integral e to the u and now half du. And that is same as half and antiderivative of e to the u in terms, now with respect to u is same as again e to the u plus c. Now you can replace u with that term, then that will be the final answer. Okay, for this one, now here, okay, that is form of f and f prime, so that you can solve that way. But for this one, we'll try to use u substitution. Now u equal 1 plus e to the 4x, then du equals same as e to the 4x times 4 and dx. Right? So here the given integral is same as integral, and now 1 over u, and remainder part e to the 4x dx is same as quarter of du. So that is, now quarter can go out, and 1 over u integral will be logarithm of u, right? And plus c. Okay. From this one, here the quarter, and now logarithm 1 plus e to the 4x is always positive, so that you don't need the absolute sign 1 plus e to the 4x. Okay, plus c. That's the final answer. Okay, we have here now recall from section 30.8, and derivative of a to the x is same as a to the x logarithm x. We got that one from by using logarithmic differentiation. Okay, let's do it here. Y equal a to the x. For the function, we may apply logarithm both sides. Then natural logarithm of y equals same as natural logarithm of a to the x. By using power law rule, we can get that one is, now x can come out and logarithm of a. Okay, now we differentiate. Then here logarithm y will become y prime over y, and right side this is constant and this is simple x term, so that that'll change it into logarithm a. So that from here now y prime equal y is here a to the x and logarithm a. So we get that formula. Oh, sorry, that one is now typo. This must be a. Okay. Okay. Now, from this one, an antiderivative of a to the x must be a to the x logarithm a over logarithm a. Now, that is base change rule, and logarithm a x is same as natural logarithm x over natural logarithm a. So that if you differentiate the function, then now from this one is 1 of x, and here the constant, so you can get that one. Okay, and we'll practice this the equations. Okay, here for that one, a to the x is antiderivative is same as now a to the x, and okay, a is 2, so that 2 to the x Okay, here that must be 2 to the x over natural logarithm of 2, and here from 0 to 1, right? That is same as now 1 over natural logarithm 2, and if it is 1, that is 2. If it is 0, then 1, so that 2 minus 1. Okay, so the answer is 1 over natural logarithm 2, right? Okay, now for this one, here you may simplify by using change variable. For instance, if we introduce u substitution, u becomes now square root of x. Then from this one, du must be same as half. Now here 1 over square root of x to the minus half, and dx. So that one, okay, so from this one, 1 over square root of x dx is same as now 2 du, right? And once x is 1, lower bound, then u must be 1 square root of x. Once x equals 4, then u must be 2. So we are using this information to get new integral. Now integral must be done in u, not x. Yeah, u is lower bound is 1, upper bound is 2. And then 3 to the square root of x will change it into 3 now to the u, and then the remainder part is same as 2 du, right? Okay, 2 can go out, and then now integral of 3 to the u is same as 3 to the u over logarithm of 3. Now we are evaluating from here 1 to 2, right? Okay, so here the constant is 2 over natural logarithm of 3, and 3 to the u, okay, here u is 2, then 9, 3 to the 1 is now 3. So you can simplify, okay? Okay, for this one, we may manipulate that one in the top. Here, log base 2 and 2 to the x. That is same as here now natural logarithm of 2x divided by here natural logarithm of 2. That is the base change rule. Okay, now we can rewrite this one more time in this way. Here, that is the natural logarithm of 2 plus now natural logarithm of x, and divided by natural logarithm of 2. So that is same as 1 plus 1 over natural logarithm of 2 and natural logarithm of x, right? Okay, so the given integral can be changed in this way. That is same as integral from half to 2, and then now divided by x, so that is 1 over x, okay, and plus here now 1 over natural logarithm of x, and now that is on the bottom, okay, natural logarithm of 2. I'm sorry about that. Okay, that is constant natural logarithm of 2, and now natural logarithm of x divided by x and dx. Okay. Okay. From this one, you can get now here, that is natural logarithm of x. Okay. Plus now 1 over natural logarithm of 2, and from this one, okay, that is now half of natural logarithm of x squared. If you try to make here derivative, then 2 will come out, and natural logarithm x, and its derivative is 1 over x, right? So you can find the antiderivative quite easily. Now you can evaluate from half to 2. Then you can get it. Just not so complicated. You can finish it yourself. Okay, that's the end of section 7.1. Thank you.